All right, today we're going to pull back the curtain on something you've probably never thought about, but you interact with every single day. It's a process called flame surface treatment, and it's basically an invisible fire that, believe it or not, helps hold our modern world together. Sounds wild, right? Let's dive in. I mean, really think about it. Why does that logo stay put? Or, for that matter, why doesn't the paint on a car bumper just flake away after a few months? It's because manufacturers had to solve this huge, fundamental problem. How do you get things to permanently stick to slippery stuff like plastic?
And the solution is probably not what you're thinking. It's not some kind of super-duper glue or a special kind of paint. The real secret is a microscopic, perfectly controlled blast of fire. Yep, fire. They use a flame to literally change the very nature of the surface, making it ready to bond.
Okay, so this brings up the obvious question. What makes these surfaces so, well, slippery in the first place? It all comes down to a neat little concept in chemistry called surface energy.
See, materials like plastics have what's called a low-energy surface. The best way to picture this is a non-stick frying pan. You know how water just beads up and rolls right off? That's a low-energy surface. Nothing wants to stick to it. Now, on the other hand, you've got high-energy surfaces, like a ceramic dinner plate. If you put a drop of water on that, it spreads out. It wets the surface. For something like ink or glue to really stick, you need that surface to act a lot more like the dinner plate and a lot less like the nonstick pan. So, here's the million-dollar question. How do you make that nonstick pan act like a dinner plate, at least on a microscopic level? Well, this is where our hero, flame surface treatment, enters the story. At its core, it's pretty much what it sounds like. A very specialized burner passes a precise flame over a surface for just a fraction of a second. Now, the goal here isn't to burn or melt anything, not at all. The idea is to use the intense heat and the actual chemistry of that flame to alter the surface and crank its energy level way up.
And when I say precise, I mean incredibly precise. We're talking about affecting a layer that is thinner than a single human hair. The treatment is so fast and so controlled that it only changes the very, very top layer of molecules. The rest of the material underneath, it's completely untouched. It's basically a surgical strike with fire.
So what is actually happening in that tiny split second the flame makes contact? Well, it's not just one thing. It's a powerful 1-2 punch that simultaneously cleans and activates the surface.
So first up is vaporize. The intense heat acts like a microscopic pressure washer, just instantly blasting away any tiny bits of dust, oils, or other contaminants. Then, right behind it, is the second punch, activate. This is the really clever bit. The flame's chemistry actually rearranges the molecules on the plastic surface. It adds oxygen groups, which create millions of microscopic hooks that ink or glue can physically latch onto.
And the result of this 1-2 punch is a total transformation. You go from a low-energy surface that repels everything to a high-energy surface that's basically begging for something to bond to it. Our non-stick pan has effectively become a dinner plate, ready for anything.
But as you can probably imagine, hitting sensitive materials like plastic with a high-temperature flame is, well, it's a very delicate balancing act. You have to get it just right, applying enough energy to get the job done without causing any damage. In manufacturing, they call this finding the operating window.
And there really is a sweet spot. As you can see here, if you use too little flame, you don't get much of a change and adhesion is weak. But if you use too much flame, you can actually damage the surface, which also ruins the adhesion. Manufacturers have to absolutely nail that just right amount to get the perfect, strong bond.
Staying in that sweet spot means controlling every single variable with incredible precision. Things like the fuel-to-air ratio, which changes the flame's temperature and chemistry. The standoff distance, literally how many millimeters the burner is from the part. The exposure time, which is often measured in milliseconds. Even the physical design of the burner itself is a complex piece of engineering. This is serious science.
Okay, so now that we know the science behind it, let's talk about where you can find this invisible process out in the real world. And the answer is just about everywhere.
The paint on plastic car bumpers is the classic example. It's all over the packaging industry, making sure the labels on your shampoo bottles don't peel off in the shower. It's absolutely critical in the medical field for applying special coatings to devices. It's used in composites, in electronics. Pretty much any time you see a tough, durable print or a strong bond on a modern material, there's a good chance an invisible flame made it possible.
So why this method instead of, say, using messy chemical primers? Well, for starters, it's much, much faster. It's easy to build right into a high-speed production line, and it creates almost no chemical waste.
For the kind of massive scale that modern manufacturing runs on, flame treatment is often the cleaner, faster, and just plain more efficient choice.
So the next time you see a logo that won't scratch off or paint that doesn't chip, you'll know the secret. It wasn't just the ink or the paint, it was the invisible fire that came first. It's a great reminder that our world is just packed with hidden science, making everything work. Which leads to a pretty cool question. What other invisible processes are out there quietly shaping the world all around us?